appointed hour. I'm scanning my screen here for Tony.
I'm here. I'm here.
Oh, you are.
Yeah, but I'm the sole individual in 295, except for the computer tech
Oh,
and Alan. Yeah.
I see. That's why you're not. Okay. Well, perfect. Why don't we go ahead and get started then, Tony?
Yeah, sounds good. Okay, before I introduce Jean, I'd like to make an announcement that next week we have Zhongwen Zhang from Caltech, who's going to be our speaker. We don't have a title yet, but Zhang is a seismologist, so expect an earth-shaking presentation. It will be another virtual lecture. Jean told me that he did not like long, detailed introductions, so this is what he told me to say. Jean is a geophysicist that does seismic imaging of the Earth and geodynamic modeling. He's most interested in understanding continental tectonics and volcanism by bringing geology and geophysics together to make informed stories. He received his bachelor's and his master's from University of California, Riverside, and he got his PhD from Caltech. Now, I'd like to add a couple of things. Jean has recently retired from the University of Oregon, whom we play on November 20th, go Utes. And I'd like to mention that I first met Jean when he gave a presentation at the University of Colorado on the tectonics of the Western United States. I've always remembered that presentation because Jean was able to assimilate massive amounts of geological and geophysical evidence into a comprehensive story about the tectonics of the Western United States. Today, Jean will speak to us about how lithospheric instabilities made the Columbia River basalt eruptions so big. So go for it, Jean.
Okay, thanks. Let me get this talk up. Okay. Okay, well, looks like there it is. Wonder if I can remove some of this stuff from my screen, or just live with it, I guess. Anyway, well, there's the title, which you just heard. And you know, I've heard that people rarely remember one thing from a talk. So if there's one thing to remember, it is the title. Lithospheric instabilities made the Columbia River basalts large. Of course, I'll say much more than that, but that's maybe the main point if you remember anything. And I'd like to give my entire talk in one slide just so you know where I'm going, because I will be saying probably too much by the time we're done. During the Cretaceous, there was flat slab subduction beneath the Pacific Northwest, and I think just about everywhere in the western US during the Laramide, and that a fragment of that slab was left behind eastern Washington and eastern Oregon. That's going to play a key role in all this. And then around 17 million years ago, Yellowstone arrives, and with Yellowstone, the melt that it generates gets between the slab and North America and allows that slab to delaminate. Okay, and it's going to delaminate from south to north, and as it delaminates, the basaltic crust of that slab is going to eclogize. And as it eclogizes, that's going to be an important part of causing or driving the delamination. It's going to peel back to the north until it gets to Washington, where it stops. And we image it at the state line now, and I think it stopped there because once you get to Washington, the basaltic crust suddenly becomes much more shallow, and it didn't get the sufficient pressure to eclogize. Another part of this story, another piece of the foundering, is when this slab rolls underneath the Wallowa batholith, that root, that very dense root, is going to fall out and allow the Wallowas to come up and drive a lot of crustal flow, actually, making this bullseye structure. So there it is in one slide. Okay, a few comments to start. there's this observation that flood basalts typically are the start of a hotspot track. And if you can find a hotspot track and take it back to its beginning, you find a flood basalt. So I think people like Bob Duncan and Mark Richards have come up with this very simple, elegant model of plume heads and tails. That is a instability from the core mantle boundary starts to rise. As it rises, it inflates because it's hard to push this mantle out of the way compared to the rapid filling of this plume head. So as the plume head gets near the surface, you have a very large plume head that is uplifting the surface of the Earth before it impacts. There's an observable that predicts. And then it hits the lithosphere and you get a flood basalt. And then as the plate moves away, you're just left with the tail feeding the hotspot track. I'll add that this is not the CRB, the Columbia River basalts. So I add a quote here from Leo Tolstoy. Theoretical plumes are all alike, but each observed plume is different in its own way. Okay. Well, to add this, kind of a side comment in a way, but you know, you wonder, are flood basalts really a good record of plume activity? And in particular, we think of large flood basalts being associated with large plumes. But I wonder, it seems like when we look at each of these flood basalts, they're either at spreading centers in the ocean when they start, or they're around the periphery of a craton, if they're in continents, typically. So if nothing else, it looks like the lithosphere is an important controller on the size of the flood basalt. This, of course, makes understanding plumes more difficult. But at the same time, I think it says a lot about what the lithosphere is. We have these big events hitting it, and how it responds is a good natural experiment to study the lithosphere. Okay, the CRB provides one particular case study. Okay, so on with my talk. I just have to introduce, I've been working on this problem for quite a while. You see a whole lot of students and postdocs who've worked on it, and my Caltech collaborators, Rob Clayton, who actually was my thesis advisor, and Jorge. Okay. Speaking of the Columbia River basalts, here's a list of strange things. First, there is an absence of pre-eruptive uplift. It will be uplifted after impact, but not before. The next thing that has often been discussed is the CRB got off track rapidly. First eruptions down here with the Steens, and it's right on line with what you'd expect for the Yellowstone hotspot track. But very quickly, magmatism migrated north, so they went a few 100,000 years as erupting up near Washington even. So what is the cause of that? And furthermore, the largest eruptions were the Grand Ronde. So it basically got large at the very end, not counting the final dribs and drabs. Also interesting, I think people who think about it now, that Yellowstone was already active before North America overrode it. In fact, it created the large igneous province that now is the Coast Range from Central Oregon to Vancouver Island, and up to 30 kilometers thick. So it seemed to be formed on a spreading center off the coast of North America, and then all that got swept up by North America. So the Columbia River basalts are really the reemergence of this hotspot. It is not a plume head from the core mantle boundary. And finally, I mentioned here where many of the Grand Ronde basalts erupted, you know, Matthew Morris's area, we see this strange bullseye structure, the Wallowa Mountains surrounded by a moat, surrounded by an uplift. And what is that about? So I'll get to a lot of that. Okay, plume meets lithosphere. I say lots of details to follow. But let me start by saying that there are three reasons why I think there is fair-bound lithosphere beneath Eastern Oregon and Eastern Washington. First, I think as has been discussed by people going back to Peter Bird and Bill Dickinson, the laramide orogeny had thrust faults and monoclines going all the way up into Montana and across Montana and even into South Dakota. So quite impressive, usually attributed to a flat slab just based on the tectonics alone. Here's a more recent paper by Barbara Karpa. Okay. 2, the magmatic history. And to me, this is remarkably simple and indicative. Flat slab stops volcanism. It basically separates North America from the ionosphere, and we have times where there's crustal thickening based on the thrusting, but no volcanism to speak of. Okay, that lithosphere is hydrating North America and probably thinning it. So when it finally comes off, we get extremely vigorous volcanism. So from nothing to really vigorous is quite a transition, and that is the Ignimbrite Flare-Up. Okay, and to go through the history quickly, if we go back to laramide times, really it was amagmatic. A little bit of Colorado mineral belt volcanism, but really very small. Many people have argued this is because of the flat slab. Now it's starting to come off. It comes off first in the Pacific Northwest. So here we are 50 to 55 million years ago, and we have this volcanism, the central Oregon volcanism that we're talking about a few minutes ago in the Clarno starts at that time. Pasco Basin has a big volcanic event at its base and the Chalice flare-up. So here we go. The slab was flat, now it's coming off as we're starting to see the foundering event of the flat slab. Okay, and if we follow forward in time, the basin range experiences the Ignimbrite flare-up. And so the slab has come off of many areas in the Western US. One place that did not experience any volcanism is Eastern Oregon, and I should have brought that up to Eastern Washington a little more. So the lack of volcanism there to me indicates the slab did not come off. But at about 16 or 17 million years ago, suddenly we get lots of volcanism here. This is a Climber flood basalt event. So that is the slab finally coming off of Eastern Oregon. So tectonics says the slab was under there. Volcanism says the slab was under there until 16 million years ago. The third line of reasoning for flat slab is we actually image it. Okay, here's a cross section, for instance, and there's what a slab looks like. That's the Juan de Fuca slab. But here is the slab dangling now beneath Idaho. Okay, that has to be Fairlawn lithosphere. It came off, allowing the Chalice flare-up to occur. So the general picture that I have for this is at flat slab time, the old volcanic arc in Idaho is now inactive. Okay, but then we start subduction at Cascadia with the accretion of Silesia. The slab comes off of Montana and Idaho to allow the volcanism to occur. So there's coming off, and now we see it dangling beneath Idaho today, and there's the Juan de Fuca today. Okay, before I go on, I'd like a few quick slides on mantle tomography, or at least how we interpret mantle tomography, to make this more clear. So here we are well below the lithosphere. And generally speaking, where it's blue, you see the seismic velocity contrast. Where it's blue, it's seismically fast. And if it's more than 1% fast, the only explanation we have based on the mineral physics is that that rock is cool. So you see a lot of cool mantle like the Juan de Fuca slab and other cool bodies around. Okay, the only place where you make coolness in this earth is at the Earth's surface. So this has to be lithosphere. Okay. Furthermore, if it's west of the Cretaceous arc or the hinge line, the Paleozoic hinge line, there is not great thicknesses of lithosphere, North America lithosphere, to draw upon. So the material out here, the high velocity mantle out here, really has to be slab that's oceanic lithosphere, not North America lithosphere. And the only possibility for oceanic lithosphere in this region really is Fairlawn slab. Remember, we had flat slab at one time, so any earlier lithosphere would have been swept away. This is all post-Laramide. So hopefully what I've convinced you of with that is, if I get my mouse back here, is that all this lithosphere is pieces of foundered Fairlawn slab or ongoing subduction of, well, Fairlawn slab that we now call Juan de Fuca. Okay, back to the CRBs. Okay, they started about 16.7 million years ago down in Southern Oregon. Very rapidly, 100,000 years, you see them erupting up in the western Snake River Plain, and they kept propagating north until you get up to northeastern Oregon. Okay, that south and north propagation, I think, is telling, and along with the propagation of volcanism is propagating uplift. And you just see that right in these flows. The Steens Pond did here. The Imnaha did not go down here. It came further north, actually all the way into Washington. The Grand Ronde stayed away from this area and went further north and covered much of Washington, flowed to the Pacific. And then the last flows did not flow down here. This whole area was elevated. We see these flows starting from Idaho and flowing all the way to the Pacific and staying away from this uplifted area. So this area uplifted, but the bullseye structure was not here at that time. I'll show you more about that, but you see over here, Saddle Mountains and Wanapum flows flowed right over where the bullseye is. As it should be here, but it's covered in my screen, so I can't quite see it there. Okay, so our basic model. We sort of have this flat Fairlawn slab extending down into Southern Oregon. I forgot to mention the tear that would have truncated it here, but the plume comes up in that vicinity, and we have this melt-enabled delamination. Okay, for delamination to occur, we got to detach this slab from North America, and a sill would be a very easy way to completely detach it, and the slab starts rolling back in a genuine delamination kind of style, south to north. And here's what we see today. It's actually detached. So you see a little cartoon here in this south to north cross section where I'm envisioning the slab was up here where the volcanism wasn't occurring. Then as it rolls back to where we image it today, the volcanism propagating north with it. Okay, so kind of a quick summary. Laramide slab was flat, amagmatic till 16, south and north volcanic propagation, and surface elevation propagation, along with the CRB and the tomography, all suggest that there was a slab underneath Eastern Oregon that delaminated during the CRB event. Okay, all this makes a good story, integrates many pieces. It's the only explanation I can come up with to account for that combination of observations. So it looks like a delamination event of abandoned Fairlawn lithosphere. Okay, why was the Grand Ronde in particular? It erupted from this area, and at that time, I gotta say this is sort of a side comment, but interesting one. At that time, we had quite remarkable dilation of the crust. A crust here, 13% dilation, just based on the dikes themselves. So 13% of that crust is dike. So this area is expanding rapidly. At the same time, this area is shortening. Okay, that's work from, I guess that's Anita Grunder and students' work here, and this is Ray Weldon's work here. But what we see kinematically is that this wedge of crust is rotating out. Okay, I say wedge because it's 13% here, 6% here. You know, that's Matthew's work, and basically nothing here at that time. So we see this rotation going on. And the reason it could have rotated, I think, is because the slab got off the base of North America and it's weaker. It's also elevated and heated, so nothing's holding it together and it can move much like the deformation occurring today. The site of volcanism is propagated towards Yellowstone. We have the extension over here. We still have this rotation, and now the shortening is occurring up here in Washington and the Yakima Fold and Thrust Belt. So just kind of a larger scale version of what we had during Grand Ronde time. Okay. So I basically have three subjects I want to cover today. One of them is the spherulon slab delamination. Check. Next thing I want to talk about is Wallowa batholith root foundering. And then I'll get to the eclogite. Okay. The bullseye is related to Wallowa batholith foundering. And I'll give an explanation for how this bizarre structure was created. Okay, so first, a more regional picture of Western US, or at least the Northwestern US. Here is the 706 line. If you want the strontium 706 line, this is ancient North America. These are the accreted oceanic terrains. I emphasize oceanic because they're largely mafic in their composition, but you see outlined here various Cretaceous Plutons. Okay, so these are pre-existing Plutons, pre-existing to the CRB itself. Okay, so that's the initial condition. Okay, zooming in, here are these various Plutons and batholiths. There's the Wallowa batholith right now. And work with TC Hills. You see the various basalt flows. Here are the magnetic reversals that you can identify. So these interfaces, more or less like layers of an onion, warped up over this uplift. Okay, and other cross sections would show a similar thing. Basically, the bullseye structure itself is post CRB. Okay, you do see deformation occurring during the CRB, fairly significant, but dominated by this bullseye formation after the CRB. Okay, and here are the Wallowas right now. Like I say, the Wallowa Mountains, and only this batholith really elevated 2 kilometers since the CRB. So that's a remarkable localized uplift, and it's associated closely with the granite body itself. Okay, so here you see on top of the Wallowa some of the CRB flows, and that flow you see at the bottom of Hell's Canyon, just a few kilometers away. Okay, if that uplift isn't convincing enough, here's some geochemistry. I'm not a geochemist, but here's how I understand it. Yttrium really likes to go into garnet. Okay, so with the creation of a dense garnet-rich root, you're sucking all the yttrium out of the granite and putting it into the root itself. So here, Leland O'Driscoll made this compilation for me with NAVDAT data. These are Plutons from around the Western US, the Peninsula Range, the Sierra Nevada, and the Wallowas. And you see the Wallowas in particular are very anomalous for the very low amounts of yttrium, so we infer a very dense root. The spiderograms show a very similar story. The latest stages of the Wallowa batholith are quite exceptional in the degree of yttrium and rare earth element depletion. Okay, so we envision from the geochemistry a very dense garnet-rich root underneath the Wallowa batholith. Okay, now as this spherulon lithosphere delaminates heading north, at some point it peels back underneath this dense root that always had slab under it ever since it was created, and suddenly it's free to founder. So that's going to be the second event, and now it's not the spherulon lithosphere itself, it's a piece of crust that is foundering beneath the Wallowa Mountains. So in terms of making the bullseye, there are two parts of the story. One, this regional uplift associated with the foundering of the spherulon slab is producing this regional uplift around this region. But then there are a host of crustal processes that are going to be very important. So let me move on to those. Here's a cross section of the crust as I envision it in cartoon form. Here is the high density root, the low density granite. And as magma is working its way north, you have lots of dikes, but you also would produce a sill, and the sill would find this area of deviatoric tension between the high density root and the low density granite and inflate that. And we think we image that, this is from Jorge, at about 9 kilometers. That probably is the sill that separates the batholith from its former root. Okay, the root is going to fall out, Okay, and as it falls out, we have a hole left behind, and the crust is going to flow into that hole. So the overall topography we see today, the Wallowa Mountains themselves came up because we unloaded them. This dense root is gone, but the lower crust had to flow into this hole, sucking it out from the surrounding region, making this moat. So regional dome, Fairlawn lithosphere foundering, and maybe this sill, but then the Wallowa uplift and the moat superimposed on top of that. So emphasizing that here are the mountains, here's the Wallowa normal fault, and here's a view of the Wallowa Mountains from terminal gravity brewpub. And you see that as you approach the Wallowas, the land actually goes up. It's not just the land in general, you see the CRB flows themselves go up. This is the only normal fault I know about where the hanging fault dips up towards the fault and not down. I think at Salt Lake City, you're very aware of the Wasatch Fault or the Teton Fault. Usually you have very deep basins in front of the uplift. Here it's just the other way around. And the explanation for that, I think, is that this crust got sucked out and this whole area just subsided with the crustal flow into the hole. So I think we call, where am I here? So we've dubbed this the abnormal fault. I think that word probably came from Matthew. Okay, so a local summary at this point. Fairlawn slab beneath eastern Oregon and Washington. Yellowstone arrives and delaminates that slab. Basically, the melt provided by Yellowstone delaminates it. As it delaminates, it rolls back to the north. It sucks Yellowstone plume to the north. So volcanism propagates to the north. And when it delaminates underneath the Wallowa batholith, the heavy root confounder, exciting these crustal processes of lower crustal flow, Wallowa Mountain uplift. Okay, so there's two of the subjects. I want to get to the eclogite-driven delamination next. Okay, and here's an image that Alan Levander provided me of the LAB, the lithosphere-asthenosphere boundary. And you see the lithosphere is quite thin. Underneath you guys, for instance, underneath Eastern Oregon in particular, underneath Eastern Washington, extending just down into Oregon, it gets quite a bit thicker. Okay, you see it's down to about 90 kilometers or thereabouts, whereas beneath Oregon, it's much shallower. To me, this is a slab has come off of Eastern Oregon. It's still beneath Eastern Washington. We image it here, but also emphasize there has been no real volcanism here as well. One of the few places in Western US where there hasn't been volcanism. And of course, if you know the CRBs, there are dikes that have propagated up here. And so there is some volcanism that propagated in from the side, but no volcanism from beneath this area. Okay, so we still see slab here, and that leads to the question, why did it stop the delamination? Why did it stop when it got to Washington? Well, a few side comments. I want to say a word about convection and delamination in particular. It takes two things to occur. The force driving convection needs to exceed the strength resisting it. We've talked about the low strength, the melt that got in between the slab and North America and cut it loose, but we need a slab negatively buoyant so that it can actually have a force that drives that downwelling. That I'm going to attribute to the oceanic crust that eclogizes. Okay, and a few words on ocean lithosphere. For relatively young slab, here's a simplified cross-section, a basaltic crust, and the mantle lithosphere of the slab and the asthenosphere, with various densities assigned to these. Things may be more gradational, but this is approximately right. The thing to note here is that the slab itself, compositionally speaking, is buoyant compared to the asthenosphere. That's because you've taken the basalt out of it and to make the crust. Okay, that is, you consume garnet and you took iron up and left this depleted mantle that is, halfway to Craton. Okay, and of course the eclogite is much more dense than the asthenosphere. So those are the two real buoyancy anomalies. This, if I rewrite that in terms of buoyancy anomalies compared to the asthenosphere, what we see is the slab itself is compositionally buoyant. The whole of the lithosphere is buoyant with the basalt on it. And as it subducts and the basalt eclogizes, it's negatively buoyant due to the basalt turning to eclogite. If you get rid of that eclogitic crust and just have the slab without its crust, it's neutrally buoyant. It's both thermally negatively buoyant, taking a temperature here of 350 degrees average across the slab. Okay, so it's negatively buoyant due to temperature, positively buoyant due to its depletion, and for a young slab, it turns out to be nearly neutrally buoyant. Okay. Okay, so what I imagine, Yellowstone comes up, the melt comes in and starts detaching the slab. That heat allows the basalt to get over the kinetic barrier that's resisting its transformation. It eclogizes and it starts to delaminate. And as it delaminates, it eclogizes at the hinge and that's peeling it off. The crust below that would not last long. If this is not really subducting and going down rapidly, that crust is either going to melt off or slide off. You know, I think a coworker, Kirsten Nicolaisen at Whitman, has been modeling some of the basalts and sees the evidence for this melting, but much of it probably just slid off, you know, as Cinti Lee has suggested for slabs. Okay, so I envision eclogite right where you want it to help delamination, and then it's gone. Okay, and I want it to be gone. I'll show you later why. So here's a little cartoon of it. Basalt, okay, and basalt, but it eclogizes at the hinge, and then it's gone. It's driving this peeling back or delamination, driving Yellowstone in, and then when it gets to the Washington-Oregon border, suddenly the crust gets much thinner. Okay, here's just a map of crustal thickness from Hayengao, and you see it's about 25 kilometers. So my inference is then as this is peeling off, when it gets to this thin, or I should say near surface oceanic crust, it's too low pressure to eclogize, and it kind of aborts the delamination at that point. And so you now see the slab hanging beneath this area, and you see very thick crust right where it's hanging. The reason this crust is very thin, maybe this is a side comment, but an interesting one is here's an image from Sandra Wild's paper, and you go back to 60 million years ago, British Columbia was against the Klamath Blue Mountain liniment. Okay, so this is all, there was no embayment here at that time. But then British Columbia slides north, presumably because of the very oblique Kula or resurrection plate subduction, pulls British Columbia north and creates the Columbia embayment. So this is the edge of North America at that time, slab subducting underneath here and going down. Okay, this left behind hole, if you want, in the crust is where the crust now is very thin. Very similar actually to the inner California borderland. Okay, so here's what we see now. The slab is peeled back. It's hanging out here. It's broken off, but I think it's not going anywhere because it's crustless. And so it's essentially cool, but compositionally buoyant in that this is neutrally buoyant, just hanging out. But this eclogite load is pulling down the crust, and you see the crust thickens quite remarkably here by 15 or more kilometers due to this load. And if we look at the crustal flow that we infer from the crustal anisotropy, and this is Jorge's work, we get this map actually extremely similar to what Fan Chi got for crustal anisotropy, which kind of indicates the flow direction. Here's where the thick crust is. Here's where the Wallowa batholith was. And you see lots of indications of flow very regionally, to my astoundment actually, flowing into this area where the crust is thick. Maybe I shouldn't have been too surprised, that's a large volume of crust that exists right here. It was pulled down recently. If that's the last major strain event, it's going to have to draw upon a lot of crust to flow into that area. But that's what we see in terms of the crustal anisotropy, is evidence for crustal flow into this area of subsidence being pulled down by the eclogite. That's the inference. Okay, and so here's the model. Actually, it's quite interesting, I think, where you have something pulling down the moho. It pulls it down, it thickens the crust. The crust has to flow in response to that. It's just a volume requirement. So we get a lot of parabolic or Poisson flow into this area. There's been a lot written about horizontal flow in the cenosphere driving Western US tectonics, and we see no evidence of that. I think the cenosphere is just flowing beneath the lithosphere, doing nothing. It's the vertical loads that are driving the crustal flow. So we've dubbed that the waterbed model. Okay. So here I think might be about my last slide. A quick summary. Once again, Farallon lithosphere, Yellowstone arrives, delaminates that lithosphere, and it rolls back south to north. It has both the requisites of a zone of weakening and a force pulling it down, and it just continues to propagate to the north, right under the Wallowa batholith, allowing it to founder, and then it stops where the crust gets thin. And where this Wallowa batholith founders, we see the bullseye created, the moat in particular, and the Wallowa uplift. And where we see the eclogite right now, north of the Wallowa batholith, underneath the state line, we see this extremely thickened crust pulled down by the eclogite. So that's it. I'll be glad to take questions.
Boom.
Yeah.
So
Thanks a lot. Thanks a lot, Gene. There's no one here except me. So the questions will have to come from everybody that's online. Does anybody have any questions for Gene? Let's see.
we need a pub and a beer.
Yeah, that's what I said. You should have come.
I really wish I could have.
I think we can see the view here.
I'm trying to get a view of everyone, but is there something in the chat? Did somebody ask something in the chat?
Yeah, I say I have a question.
Okay,
Let her
go,
go.
Fanchi.
Yeah, so it's every time I hear you talk, it's always like, oh, there's so many different components all kind of fitting, and but there's still a couple of things I'm curious about. So maybe it's not related to this, but I hope like maybe you can provide some insight. So one of it is like when I was doing my PhD, I always heard like there's some connection between the Newberry and the Yellowstone. So do you have any insight on that?
Yeah, it goes back actually to a suggestion. Let me see. Am I still sharing my screen? I think so. Yes.
Yep.
That Dave Draper made now at NASA, I believe. But here's the mantle at 200 kilometers. This at 250 kilometers is the slowest mantle in the Western US. Where did that come from? And what Dave suggested was the Yellowstone mantle, when it arrived here, the Yellowstone propagates this way, but this big blob of hot mantle, if you think about subduction going on over here, corner flow would drive the asthenosphere towards subduction. And it's oblique subduction, so it actually drive it in this direction. So he's suggesting that Newberry is the Yellowstone plume accumulation that's been pulled or sucked or whatever from southeast Oregon towards the subduction zone across Oregon. So that's the Newberry trend, and Newberry right now is active here. So that's the best idea I could think about. Not my own idea, but Dave's.
Okay, thanks. And just quick, another thing I'm just curious about is like, so usually like when I think about delamination, it's like cold stuff, heavy eclogite, and then it falls down. But here you actually have Yellowstone hot stuff also interact with this. So I guess my question is why the hot part of the Yellowstone interact with only the eclogen instead of also kind of heat up the slab itself. And so how I guess I'm not sure, like mechanically how it kind of fill into the gap and make things kind of separated from the crust, I guess.
Yeah, no, the thought is, of course, the slab is, still leftover coolness from the Farallon slab. To warm it up with Yellowstone is going to require conductive heating into the slab. That's going to be a fairly slow process. But as Yellowstone plume ascends and melts, that melt is going to pond. And one place you would expect it to pond is at the moho, basically, or right above, or maybe above or below the oceanic lithosphere, or crust, I should say. But it's basically the sill being created by Yellowstone ponding that does the actual detachment. I showed you a little model there at one point. It's actually a model that Jonathan ran showing what happens if you put melt into the system. It go right there where the density contrast is high between the slab that's eclogizing and the North America crust.
Okay, so basically the argument is the kind of conductive warming is just much slower than this kind of injection of the melt.
Right. And and we still see, I mean, there is the Wow anomaly. That is, I showed you cross sections that is the slab that's hanging out there now. That is lithosphere. There's nothing else that really can be. But it's just hanging out neutrally buoyant, just like this stuff is. It's all Farallon slab without its crust.
Mm-hmm. Okay, all right, thanks.
Yeah, I should say, to add to the response, is delamination in general, where you don't have melt around to decouple it. When people model it, they rely on a very mobile lower crust so that the crust itself can flow and allow this thing to delaminate. But people really in their models have problems making that work unless they make the lower crust very low in viscosity. I think melt enabled delamination is probably a very common event. Either that or convergence forced delamination.
Okay.
Anybody else?
I have a question.
Sure, thanks.
I saw in one of your figures about 50 million years ago or so, there's something like a mid-ocean spreading ridge off the coast of Washington and Oregon.
Yes.
I just as a broad brush question, what role could slab windows being subducted play in this?
Yeah, no, good question. Here's an image, I think. In fact, that slab window is what I think Torkelson and some of the people at Simon Fraser argue is the source of that volcanism. I think where we want to put the spreading center now to give rise to this northward transport has it a little too far north for that. But if you imagine taking this spreading center under the continent, it would open up this V-shaped region where you would be getting some volcanism. So it's possible that's what's happening underneath British Columbia is related to this opening slab window to some degree. We do image, well, I just left it, I guess, behind, this piece of slab fragment that looks like it rolled back. This rolled back from beneath Montana to here. This probably rolled back from beneath British Columbia to here, okay? And Paul Umhofer and Miller are working on that story right now. That'll be presented at GSA. So that would put slab here. And if there's slab here, there isn't a slab window here. Okay, and this clearly has to be Farallon lithosphere in my mind as cold mantle. I gave that argument. So the slab window, I think, probably is somewhere north of the international border.
Okay, thank you.
Sure.
Anybody else? Oh, I'm still muted.
Nope, I think you're unmuted now.
Okay. Anybody else have any questions? Okay,
Sure, I'll ask one.
sure.
Thanks.
Okay. So, Gene, could you say a little bit more about that weird rotation in the geodetic data up in the Pacific Northwest? You sort
Yeah,
of explained it as being related to the Yellowstone hotspot track and the kind of the dike intrusions following that. But the southern part of that was a long time ago. And secondly, what's happening in the, out in the middle of Oregon and Washington to,
yeah.
push that back around to the north.
Yeah, geodynamically, there are several things going on at once in this area. If you think about this as a plate, the boundary condition here in the long term is south and north traction. Subduction subducts, pushes it in, which we see now, earthquake happens, it jumps back out, pushes it back in. But there's always this south and north traction, that Kellen Wang talks quite a bit about, producing, north-south compression in the Coast Range. It's clearly moving north. Actually stopping right at the Straits of Juan de Fuca. Vancouver Island isn't moving north, but it's being pushed to the north by oblique subduction. Okay, you go back to Yellowstone, and this whole zone, the Basin Range and going right through Yellowstone now has been weakened by volcanic activity, Ignimbrite Flare-Up and Yellowstone. And on top of all that, we have this very high potential energy in this area. Okay, so this stuff is sliding downhill. Okay, in fact, the Snake River Plain itself, there are models talking about, the extension going right across the Snake River Plain into the Basin Range up here. And that's not happening. You have some diking into craters of the moon, but as Mark Anders points out, there's no extension in the southern part of the Snake River Plain or in the southern Basin Range here now, or the northern Basin Range. Not until you get farther south, you have extension. So this potential energy is actually pushing down, compressing the Snake River Plain and pushing the whole thing this way. So a combination of side traction, weakness, and potential energy from high to low are all acting to move the Pacific Northwest in this fashion. I should add to that, actually, as I'm thinking about it, there is very little compression on the subduction zone in a regional tectonic sense. So we see all this extension right now. And this is Ray Wells' idea, basically. The Sierra Nevada is, because of Pacific plate motion, Sierra Nevada is being entrained and pushed this way. And the Sierra Nevada is pushing the Coast Ranges north as well. Okay, so all that's acting to produce this tectonic picture. I don't think anybody has put the time to actually stop and model all that, but those are the elements. Yeah, no, good question.
Anybody else?
Very awkward environment to ask questions, I know.
Yeah, it's crazy. Okay, then I'd say let's thank Gene with the virtual hand clap. And yeah, thanks a lot, Gene, for coming. Again, another great story.
Sure.
Really
No, it's a, as a Zoom presentation, I never know how's going on the other end.
Well, I don't either. I'm here by myself. It's very funny. It's like being in a movie theater all alone.
I hope that made sense to people.
So wait.
Mm.
Yeah, you got another few comments.
Is there more comments? Let's see.
So, okay, Gene, thank you very, very much. And
Sure.
I hope to see you in the future. Okay.
Yeah, I expect you will. And
All
I can
right.
hang around if there are any trailing questions.
Okay. Thanks.
Thanks, Gene.
Sure. Thank you.
Thanks, Gene.
Yeah. Yeah. Good to see you, Jim.
Good seeing you. Interesting talk.
Oh, thanks.
I think I
Thanks,
followed.
Gene.
Hi, Matthew.
Most
Good
of
to
it.
see you again.
So Gene, actually, I do have some couple of follow-up questions. I mean, is there any like gravity signal that should be able to observe with all this going on?
I've looked at the gravity. I'm sure the gravity is consistent, but it's quite complicated. And I think that really makes sense to the gravity to have to sit and model what we know the crustal structure to look beneath it some. I think I can say that these very large blue anomalies beneath Idaho and beneath the Laos, or beneath the state line, I should say, you would expect them to be big, high density anomalies, and you don't see it in the gravity, which I think is what I would expect, because I think they're neutrally buoyant. Like I say, that curtain beneath Idaho has been hanging out there for 50 million years.
So there's no, I guess you don't expect to see any ecology in the gravity data. I guess it's hard to see the ecology from seismic data as well. So
from seismic data, it'd be hard. As a high density anomaly, underneath this area, you might expect to see it, but that's right where it's thick in the crust. So you have this low density crust right above the high density eclogite. So you got maybe a bit of a density moment, but it's going to be very hard to see that.
Yeah, that's, I can see it's hard. That's too bad.
Yeah. No, I've looked at it and tried to make sense out of it. There's nothing that I see there.
But you said it's like a thick crust and then ecology, but how thick is the ecology? Is that really not, I guess, surface way with VS probably not going to be able to resolve it, but how about VP?
We haven't really seen it, and maybe you could look at it carefully, and maybe you would see something. So without really knowing from imaging, I'll just say it's ocean crust. So I'm assuming or guessing that it may be 6 or 7 kilometers.
Okay, yeah, that's very thin. Yeah.
Yeah.
About that. Okay.
Gene, I'll ask a question, which is probably a really stupid question, but it's coming from a hydrologist. Why can you give some explanation for why hotspots like Yellowstone seem to persist for such a long time? I actually hadn't realized that the thinking was that the hotspot was there, as long ago as you indicated.
Yeah.
How do they persist?
First I say, Bob Duncan suggested that in a little GRL paper a long time ago, but Ray Wells came along and has a really great paper on that in Geosphere. It's long and complicated, but you get the whole story by looking at the pictures. So it's good. But the idea is that the core mantle boundary, or somewhere near the core mantle boundary, is heated up and just providing plume that just keeps flowing for a long time, like Hawaii. And I think in the case of Yellowstone now, I think, with Brandon Schmant, we see it down to 1,000 kilometers. And now I think Nelson and Steve Grand have imaged it all the way to the core mantle boundary. Okay, so it just looks like it's a connection between this source of hot mantle at the core mantle boundary that is buoyant and flows to the surface, and it stays hot and keeps flowing. I don't know if it'll just peter out and when that might happen, but I think that's the origin of its longevity anyway.
So do you require a continuous sort of heat source at the core mantle boundary to do this, or is the time constant of the heat dissipation just such that, lasting,
Not
50 million
good question.
years?
I think the core mantle boundary is going to stay hot. I think most people would say now that these plumes are actually coming off a layer right above the core mantle boundary, but it too stays hot. So there is a long-term source of heat. And people try to infer the temperature of the plume, and it does cool off as you come up, apparently. And then based on the imaging, what Steve Grand sees, and it's not a vertical conduit coming up, it winds around. It basically is coming from farther south and drifts in the mantle wind, if you will. And as it crosses the transition zone, 410 and 660, it seems to be interacting with it, so it's actually disrupted. So we see the 660 affected by the thermal anomaly, but the 410 not. and there seems to be a break in it there. So it really could give rise to pulsing or irregularity. So it's not a simple straw from the core mantle boundary at all.
Yeah.
It seems like the heat source is quite persistent, and in an overall long-term sense, this persists. It'd be interesting. I'd like to hear what Bob Smith says, because he's been, from the surface trying to image that plume for a long time, and he gets it down a ways. We get it down a ways, but I think not until the global imagers got a hold of it did we really have convincing evidence that it goes way down deep into the lower mantle.
Interesting.
Yeah.
I have another quick question with the Yellowstone hotspot. Is kind of with the timing with that, was that after subduction of the Pacific plate already began, or Juan Fuca and kind of crossed
yes.
over?
Yeah, no, the history briefly. Let me see if I got a slide that might say something. Well, this will work. I went through this quickly and even forgot to say a thing about this side, I think. But if you go back to 55 million years ago, you had a situation like this. The volcanic arc that existed in the Western US is now quiet because the slab is flat under it. Plate subducting, and probably a Kula or a resurrection plate subducting. And then the seamount chain that's being created here. Oh, good grief, I got a better slide someplace down here. Sorry. Here we go. So here we go. At 60 million years, there's Sandra Wild's picture. British Columbia is back against the Klamath Blue Mountain lineament, spreading center, Yellowstone, forming two big, large igneous provinces. Okay, this is going to be the Coast Range, and this is going to be Yakutat. Okay, and then here's a figure for Wells showing it at 50 million years, basically, and you see this being accreted to the Coast Ranges. Okay, pull this north, get a Columbia embayment. Okay, and then this chokes the subduction zone. And when it chokes the subduction zone, the subduction jumps from here, the old embayment, to the Cascadia subduction zone. And so now we start Juan Fuca subduction here. It continues down here, it is going all the time, but up here we jump the subduction zone out to Cascadia. Okay, so now we start Cascadia subduction, and Ray Wells and Duncan and people look at the volcanism here and they see 3 times of volcanism: Yellowstone volcanism, initiation of subduction volcanism, and then Yellowstone volcanism again, as this whole package overrides Yellowstone. Okay, and then as this whole package buries Yellowstone deeper and deeper, once Yellowstone is under that slab, let's say beneath 150 or 200 kilometers, it's too deep to be decompression melting. So you have hot plume, but no melt. So Yellowstone then has to find its way through that slab somehow. And I gotta say, all geodynamic models suggest that Yellowstone is incapable of doing that. It's just a puny couple hundred degrees compared to, this big slab. It's actually got to find a tear in the slab before it comes through. And, to me, that tear occurs because it found that southern tear. When this accretes, flat slab subduction here, new normal dip subduction here, a tear in the slab here. And when this whole package moves north, then Yellowstone finds the tear. Okay, that was probably too much. But yeah, the simple answer is yes, there is slab between North America and the Yellowstone plume. And then the Yellowstone plume has to find its way around that somehow.
And because that high pressure over the Yellowstone hotspot, would that mean it would be unlikely to have any interactions with Cascade volcanics or any influence?
People argue about that, but the geochemists who look at the early Cascade volcanism so far have not seen evidence for Yellowstone. That's Ilya Bindeman and Anita Grunder and people like that. However, I think Ilya in particular argues that some of the volcanism occurring here before the CRB show signs of maybe being Yellowstone. I don't know if you know Oregon, but some of the stuff behind Cascades. And I think Spielman and Bindeman have some papers on that. So maybe little dribs and drabs we're getting through somehow, and maybe not. So I think you probably got more of an answer than you wanted.
That was great. Thank you.
Yeah. Okay.
Any new story on Wyoming crater or Colorado plateau?
Well, I guess you know the story of Wyoming. I almost talked about that. I guess for those that don't, the Shatsky conjugate subducted under California underneath the Colorado Plateau and is now living abandoned under Wyoming and parts of the Colorado Plateau. Really cool story. Fan-Chi knows that story, I think. The uplift of the Colorado Plateau, I think, is a multi-stage event. Maybe the first uplift associated with the Shatsky conjugate going under it. But once you start taking the slab off, then you've unloaded the Colorado Plateau. The slab is no longer there, and it comes up. And the last stage of uplift seems to have occurred more like 10 million years ago for the Rocky Mountains and the Colorado Plateau. And that's based largely on geomorphology. And it seems to coincide with the mantle Aspen anomaly, the pattern of uplift. That looks like just basically lithospheric instability in the old fertilized Colorado mineral belt.
Wait, I didn't get that. So how the mantle become buoyant? Is that like, there's nothing delaminate or anything, right?
No, I think as the slab is getting off, for the Ignimbrite Flare-Up, it was very vigorous under the basin and range for good reasons. But you also see it underneath the Colorado Plateau, and you see it coming up into the Rocky Mountains some. And when it hits the very southwest corner of Colorado, the San Juans just blow up. Okay, and that's right on the Colorado mineral belt. So the idea is the Colorado mineral belt fertilized that mantle. That is, it put a lot of basalt into it. That'd make it dense and magmatically productive. When you pull the slab off of that, it starts, it just triggers this. I sort of imagine Pac-Man eating its way up the lithosphere as the lithosphere is just dripping off, falling down. But you have to get rid of that lithosphere somehow for the San Juans to be so active.
I see.
And it's right where you see this hole now in the Aspen anomaly.
Yeah. Cool.
That's the idea. It is. I think it needs more thought modeling than that, but that's the best I can do.
Yeah. 5 years later, you can give another story on that.
yeah. That's I think a little over a year ago, or maybe more, Carl Karlstrom had a bunch of geologists float down the Grand Canyon, and every night seminars on why the Colorado Plateau came up. And that was sort of a conclusion of this floating seminar, was this sort of 3-stage event.
Okay. That's very cool. Thanks.
Yeah. I think what's anomalous about the Colorado Plateau is its total inactivity for so long until recently.
Sounds like a great excuse to do a river trip down the Grand Canyon.
Indeed, very attractive.
How old is that volcanism in Colorado, like Platoro and Creed and all of that?
Now, I don't know all the names, but the Colorado mineral belt stuff goes back. We'll have Chapman plots a lot of that. I hate to guess. Actually, I should know that.
I should go look it up.
Yeah, but look at Chuck Chapin in particular. He has plots of that. But then as the Farallon slab pulled through there, probably the Mendocino fracture zone really going north. So you got thick to thin lithosphere for the southern Ignimbrite sweep. Alan Glazner talks about that volcanism quite a bit. And that propagates north, so that San Juans, I think, are more like 34 million years ago or something like that.
Thank you.
Yeah, and I should know what the Colorado Plateau, what the Colorado mineral belt magmatism is. I don't. Actually, I do. I think back. It's more like 70-ish million years. Yeah. In fact, it's a part of the Shashi conjugate story, but that's another seminar. Yeah, but we do. I guess we do have a paper from 1990, from 2015, on the Shatsky story, if you're interested. Okay. There are no more questions. I guess it's time for dinner, huh?
A beer.
Yeah.
Gene, thank
Well,
you.
thanks for
Thank you very much. Really interesting.
Yeah. Well, you have a few people there in your own department that have worked a lot in aspects of this. I see Fanchi, you know, Bob Smith and Farrell, and others. So you have a good department for this.
You don't have a good storyteller like you.
Yeah.
You know, that's my job, is making stories, right? We call them hypotheses to sound important, but they're just stories. Okay, well, I might as well stop my share and say thank you.
Yeah.
Okay.
Thanks a
Yeah.
million.
Thank you
Yeah.
again.
Yeah.
Bye.
Bye-bye.
Have a good night.
Yeah, you too.
All right. I think this is